Today we're doing the chemistry of life. The chemistry of life. The chemistry of life, that is biochemistry. Biochemistry. We also have biophysics. That is the physics of biology. There is the chemistry of biology. So we know that we have established last week that we don't just have gross anatomy dealing with cadavers. Okay, we are not just dealing with gross anatomy. There is also histology. So what's the difference between gross anatomy and histology? Gross anatomy can be seen with the naked, and histology cannot be seen with the naked eye. You need a microscope for that. Okay? And then, because of that, now we have something known as deconstructionist or reductionist view. And that is, we go from up to down. We go from an organism, and the organism is made up of organ systems, and the organ systems are made up of tissues, and tissues are made up of cells, and cells are made up of atoms and molecules, organelles, and so on. These are the things that make up the cell. So now this is reductionist. We go from big down to small. Back in the day, all the science was happening up here at the level of the gross anatomy. So now we're going to be studying the atoms, the molecules, and the organelles. And we established last week that this is actually where all the disease and all the health is taking place. We said we are healthy because our cells are healthy. We are sick because our cells are sick. We are alive because our cells are alive. We are dead because our cells are dead. Why are we alive? Because the enzymes, the proteins, the organelles are working fine. If the atoms, the molecules, the organelles are not working fine, then the cell will be damaged, then the tissue will be damaged. So now, if we want to have medications for cancer treatment, the cancer treatment medication is going to be targeting some protein enzyme, a protein suppressor. We're going to be activating some enzyme or deactivating another enzyme. And enzymes are proteins, molecules, and atoms. So now we're going to be delving inside the cell and learning what's happening at the level of the chemistry of the cell. That's very important. Okay? So now, as we said back in the day, they used to have a holism. So holism, when we look holistically, going from little to top. We are now we learn, due to the reductionist or deconstructionist view, that we are actually a sum that is made up, a whole that is made up of little parts that are added together. Okay, so we have to now go into the atom, and we cannot understand what the atom is unless we know the structure of the Niels Bohr model. So Niels Bohr is very interesting because he said there is a nucleus. There is a nucleus. And in the nucleus, you have proton, and you have neutrons, and then you have protons, you have neutrons, and you have electrons spinning around. This is the nucleus. So Niels Bohr said that the atomic number equals to the number of protons. The atomic number is equal to the number of protons. So if one molecule has 2 protons and 2 neutrons, what's the atomic number? 2. And that atomic number is your number in the periodic table. So if your number is 1, that means you are hydrogen. Your number is 2, that means you are helium. You mess up with the atomic number, you mess up with the proton number, you change completely the atom from one atom to a whole different element. So you can never change the proton number. Then there is the atomic atomic mass or atomic weight, and that is the number of protons plus the number of neutrons, or we add them together, or the same thing as number of protons is the same thing as the atomic number. The number of protons, the number of neutrons, and that is the atomic number. The atomic number is going to be that these two are the same thing. They are interchangeable. If I say atomic number, I mean number of protons. If I say number of protons, I mean the atomic number. So as we said, if one atom has 2 protons, 2 neutrons, what is its atomic number? 2. What is its mass number? What is its atomic weight? 4. So atomic weight and atomic mass are the same thing. Atomic number and number of protons is the same thing. That's very important. Then we move into the concept of isotopes. What are isotopes? Isotopes. Isotopes are different variations of the same element. Different variations of the same element. So now let's look at hydrogen. Hydrogen is the same element as deuterium, which is the same element as tritium. That's very interesting. So that means if they are the same atom, that means they will always have the same number of protons. So this one will have 1 proton, deuterium will always have 1 proton, and tritium will always have 1 proton. If they are isotopes, then if they have the same proton, then that means they have something else that's different. And what is that? Neutrons. That's the neutron. So the neutron for hydrogen is 0. Hydrogen has no neutrons. So what is the atomic number of hydrogen? 1. Very good. The atomic number of hydrogen is 1. And what is the mass number of hydrogen? Is 1. Because 1 plus 0 is 1. So hydrogen has the same atomic number as its mass number. Deuterium has 1 neutron. So that means the atomic number for deuterium is how much? The atomic number for deuterium is 1. And the atomic mass or the atomic weight for deuterium is 2. Very good. That's the atomic weight. Tritium has 1 proton and how many neutrons? It has 2 neutrons. So what's the atomic number for tritium? 1. And what is the atomic mass or the atomic weight for tritium? 3. Excellent. So you see, the isotopes, they have to have the same proton number. Because if I change this into 2, it's going to become now atomic number 2, then that's a different. You can have different mass numbers, that's okay. But if you change the atomic number, you change the whole element. Then we have to understand the electrons. So the electrons are spinning around the nucleus. There are electrons that are very close to the nucleus, and electrons that are very far from the nucleus, spinning outside to the farthest energy levels. And these are the most important ones. These are known as the valence electrons. So the valence electrons are spinning outside, and these are the electrons that we use to make a bond. So we bond with the valence electrons. We don't bond with the electrons that are close. They are too close to the nucleus. So the proton is positive. So the positive charge and the negative charge closer to it, they have a very strong bond. So you cannot get that out. You cannot remove that. But the ones that are really far, they are the ones who can engage in the bonding. It's very important for you to know the difference between what's an isotope, what is the atomic number, what is the mass number, and you must understand also that the valence electrons are in the highest energy. So if you're outside, you are in the highest energy. You are unstable. Outside, you're unstable, highest energy. And very close to the nucleus, you are really stable, you have low energy. Because the proton that's plus is pulling you. You are being pulled to the proton. Okay? Does this make sense?
Yes.
Okay. Then we have so these are the isotopes, and this is the these are the valence electrons, and now we're gonna talk about the bonding. This is really important too. So does everybody knows now what is atomic number, atomic mass, isotope, valence electrons, the protons are plus charge, neutrons are zero. That's why they call them neutrons, because they're neutral. They are not positive, they are not negative. They are neutral. And what about the electron? The electron is negative. Okay, are we through with this? Yes?
What does it say on the atomic mass in that box? Yeah.
So the atomic mass and the atomic weight are the same thing. So they are interchangeable. Some people say, when they see atomic weight, they say, what is atomic weight? I only know atomic number and atomic mass. The same thing. What's the difference between mass and weight? Mass is how much matter occupies space. So my mass on Earth, and my mass on the moon, and my mass at home, my mass in the subway, my mass is the same. That's how many molecules I have. But my weight is my mass times the gravity. Mass times gravity. So the gravity of Earth is different than the gravity of the moon, is different than the gravity of Mars, different than the gravity of Jupiter, and so on. So my mass on Earth is going to be, let's say, 100 kilograms. My gravity on Earth is 9.8. So my weight is going to be 100 times 9.8. But my mass, there's no gravity attached. So my mass will always be the same. It is the gravity that's different. So that's the molecular weight. That's why there's a G in there. So the molecular weight, that's the G, is with the gravity. But the atomic mass is just a mass. So in the atomic mass, we just like this. In the atomic mass is just a mass. In the atomic weight, we multiply the mass by gravity. Or we multiply the atomic mass by gravity. Okay? But here, we use them relative. We say the relative atomic weight. But for now, for all intents and purposes, in our chemistry, we believe that the mass and the weight are the same. Okay, just for the purposes, but they are actually not the same. Okay, now we have to understand what a mole is. I mean, we cannot be doing chemistry. We cannot be doing chemistry without knowing. This is the Niels Bohr model. That you have the nucleus, inside you have a proton, then you have a neutron, spinning around them are the electrons. I mean, do the atoms look exactly like Niels Bohr model? Obviously not. But this is a close. So models help us. It's like a template. It's a template that helps us understand the structure. But it doesn't look exactly like that. If you take an atom, look at it, you're not going to see like a proton and a neutron and spinning around them or the electrons. But it's quite similar enough. Okay? All right, so now we cannot be going around not knowing what Niels Bohr model is, and now we know. We don't know what an atom is, what's the electron, what's the neutron, it's this board, now I remember. Yeah, this is gonna make all of us friends working together. Okay, Mole. Chemistry, and we don't know what a mole is. I mean, we're doing chemistry and we have no idea what's a mole. Okay, a mole is 6.03 times 10 to the power of 23, which is the same thing as Avogadro's number. Avogadro's number. Okay, this number is just a number. Is just a number. Is a standard number, like a dozen. When you say a dozen of eggs, a dozen of eggs, a dozen means 12. What is more, a dozen of eggs or a dozen of cars? What is more? They are the same. But who weighs more, a dozen of eggs or a dozen of cars? So that's the basis of the periodic table. So when we put the periodic table on the projector, you're gonna see that each element has a number. That's the atomic number, which is the number of protons inside it. Then you're gonna see AMU. AMU is atomic mass unit. Atomic mass unit. This atomic mass unit is actually a mole worth of the atoms. For example, let's say I want to make a periodic table based on the weight of a dozen of each atom. So now that number is going to represent 12 sodiums, and then weigh them. How much do they weigh? 12 potassium, weigh them. How much do they weigh? 12 boron, weigh them. 12 carbon, weigh them. But the problem is 12 is too little. The atom is so small. That's why they came up with this huge number, 6.03 times 10 to the power of 23. So now, this is not 3 zeros. That's not 6 zeros. That's not 9 zeros. That's 23 zeros. That's 23 zeros. So the 23 zeros are a huge number. So when they wanted to get the AMU for each single element, they went and they collected Avogadro's number worth of that element and then weigh it and then put the atomic mass. Then Avogadro's number worth of sodium, weigh that, then put it on a periodic table. Then calcium's, Avogadro's number worth of calcium, then put them on the scale, weigh them. How much does that come out to? Then Avogadro's number worth of helium, weigh them. And that's how the periodic table is arranged. It's based on, they all have the same number. They all are a mole, but they don't weigh the same. Like they all are a dozen, but they don't weigh the same. Dozen of eggs, dozen of cars. Here, a mole of sodium, like a huge number. That's why it's so huge. They call it Avogadro's number. So Avogadro's number worth of all the elements, weigh them, see how much that come out to. So now you see how the atoms, we're going to come back to the periodic table. So now do you know what a mole is? Any questions with this concept? How are the elements in the periodic table arranged? They are arranged based on the atomic number. So 1 is at the top, next to it is 2, then 3, 4, 5, 6, 7, and so on. Then you're gonna have your atomic number, and that is your atomic number. But with the atomic number, you're gonna see like 22.5, 15, 17, 23.3. The 2-digit number, that is your AMU, which means what?
Atomic mass unit.
Yeah, atomic mass unit, which explain it to me. How did we get the atomic mass unit?
With the Avogadro's number.
Yeah, so what do we do with the Avogadro's number? Yeah, very nice. So we took the same amount, Avogadro's number amount. Not the same amount of, the same number of Avogadro's worth. So now we can have a dozen of each and weigh it, but it's too small. Then we get Avogadro's number, then weigh it. So that number represents Avogadro's number worth of that element. The AMU underneath each element is Avogadro's number worth of that element on the scale. Okay, like 12 dozens on, like 1 dozen of eggs on the scale and 1 dozen of cars on the scale. They are both 12, but they weigh different. Here they are both mole, 1 mole. They are both Avogadro's number. So Avogadro's number is 1 mole, it's this number. So you need to know the 3. That 1 mole is equal to Avogadro's number, which is this number, 6.03 times 10 to the power of 23. So you multiply this number by 10 with 23 zeros. Yes?
So does that mean that for the different weights for each element, are you multiplying Avogadro's number by the weight of the element to get that individual?
Excellent, yeah. So the weight of the element is so small, okay? Then we multiply them by Avogadro's number to get their weight, because we are weighing all of them in Avogadro's number worth. So the quota is Avogadro. So you say, let me weigh 1 mole of sodium. How much that come out to? That's the AMU. 1 mole of calcium. Weigh that. That's the AMU. Okay? All right. So now let us move to, now we have established what an atom is, and we have established that the electrons are outside. So, what are the kinds of bonds that we can make? What are the kinds of bonds that we can make? We can make a covalent bond. A covalent bond is shared. A covalent bond is shared equally between atoms. So you have oxygen that is in the middle of 2 carbons. So here you see they are sharing equally. They are sharing a pair of electrons. They are sharing a pair of electrons. They are sharing a pair of electrons. It's like me and my friend, we rent a taxi for a whole day, 24 hours. Then I drive it for 12 hours, I pay 100, my friend pays 100. 200, we get the car for 24 hours. I drive it for 12 hours, then I give him the keys, then he drives it for 12 hours, and then we share it equally. Or we share the rent equally, or whatever. So that's what happens. That's a covalent bond. In a covalent bond, what happens is both atoms, they are sharing the electron. It's not like the electron left. That would be in sodium chloride. In sodium chloride, what happens is one electron, one pair of electron is gonna go to chloride. So it's now not shared. It is not shared now. Chloride has the electron, chloride is minus, and sodium lost the electron, then it's plus, and that's an example of ionic. That's an ionic bond. So in ionic bond, somebody lost the electron, somebody gained the electron. Leo says Ger. Leo says Ger. Leo is lose electron oxidation. Lose electron oxidation. Gain electron reduction. Lose electron reduction. Gain electron, lose electron oxidation. Gain electron reduction. So according to this law, Leo says Ger. Sodium gave chloride a pair of electrons. Who lost the electrons? Sodium lost the electron. So that makes sodium oxidized or reduced? Sodium. So sodium, Leo says Ger. Lose electrons oxidation. So if you lose the electrons, you're oxidized. If you gain the electrons, you are reduced. So here sodium lost the electron, it became positive. Remember, the electrons are negatively charged. So sodium lost the negatively charged electrons, and the electrons went to chloride. So now you have chloride minus and sodium plus. So now sodium, did sodium lose the electrons? No. Is sodium oxidized or reduced?
Oxidized.
Now chloride gain the electrons. Is chloride oxidized or reduced? Excellent. Gain electron reduction. Lose electron oxidation. Okay, there is another law that says the agent, which is very simple. Very simple, the agent. So, if you are oxidized, you are the agent of the opposite of what happened to you. So if you are oxidized, then you are the reducing agent. And if you are reduced, then you are the oxidizing agent. So if I ask you on the exam, who is the reducing agent and who's the oxidizing agent, go back, determine. Leo says GER, and after you get the process, then the reverse, then it will be the reverse agent. So for example, you have to tell who is oxidized first. Because the one who is oxidized, that will be the reducing agent. And the one who is reduced, that will be the oxidizing agent. But do not begin with which one is the agent. Begin by identifying the process, and the reverse of that will be the agent. So now, let's look at sodium chloride. Who lost the electrons? Sodium. If losing the electrons, according to Leo says GER, losing the electrons, does that make you oxidized or reduced? Who's saying reduced? It's right here. Leo says GER. Lose electrons, oxidation. Gain electron reduction. You should not be having a difficult time telling this. It's Leo, L-E-O, says GER, G-E-R. It's right here. If you lose electron, you are oxidized. If you gain electrons, you are reduced. So here, sodium gave the electrons. So who lost the electrons? Sodium. And if you lose the electrons, what process is that? Oxidation. And if you are oxidized, what agent is that? Reducing agent. Excellent. You cannot be oxidized and the oxidizing agent. You cannot be reduced and the reducing agent. Somebody else reduced you. So if you are oxidized, you are the reducing agent. If you are reduced, then you are the oxidizing agent. So here, sodium gave electrons to chloride. So sodium lost electrons, Leo, oxidation, then sodium is the reducing agent. Then chloride gained the electrons, then chloride is reduced, and what kind of agent is that? Oxidizing agent. So that is for the ionic bond. In the ionic bond, because now we have ions. If you lose an electron, you become positively charged, because we said electrons are negative. So you lost an electron, that makes you a cation, like a positive charge, cation. Because now you are positively charged. And if you gain an electron, you are an anion. You are negatively charged. So here, sodium lost an electron. Does that make it a cation or an anion? Sodium lost an electron. I'm sorry? So the sodium is what? Cation or anion? Cation. Yeah, it's a cation. Very good. So remember, we deal in terms of electrons who are minus. If I get electrons, I am more minus. If I lose electrons, I am plus. So the currency that they use in the chemical transaction, that is the electron. So they don't give $1, they give an electron. An electron is minus. So if an atom has a minus charge, that means it got one electron. And if an atom has a plus charge, that means it lost an electron. Unlike what we do with the bank transaction. If you owe money, you have a minus charge on you. And if you get money, you get a plus charge. That's because you're dealing with money. But here you're dealing with minus. So if you are minus, it doesn't mean you lost. It means you gained a minus electron. And if you are plus, it doesn't mean you gained. It means you lost a minus electron. Is that clear? So now this bond here, NaCl, is not a covalent bond. They are not sharing electrons. One gave the other one. That's an ionic bond. This one is a covalent bond. This one is a covalent bond because now they can share equally. Okay? Now they can share equally. Actually looks like that. They can share equally. They can share equally. So when they share equally, that's a covalent bond. That's an ionic bond. Then there is a hydrogen bond. Hydrogen bond is a bond that, so there are other types of, I need to tell you about covalent bond. So this is a non-polar covalent bond because the electrons are spending the time on all the atoms equally. So electrons are 50% with oxygen, 50% with carbon. On the other side, these electrons are 50% with carbon, 50% with oxygen. So that is non-polar. That's non-polar covalent bond. Now let's look at oxygen and hydrogen. Oxygen is so big, hydrogen is so small. So oxygen puts out one electron and hydrogen puts out one electron. Now oxygen is so big. Now oxygen is going to drive the taxi for 20 hours and give the hydrogen the taxi for only 4 hours. So that's exactly what's going to happen. The electrons are going to be spending more time around the oxygen and a little bit of time around the hydrogen. So now the bubble, here the bubble is similar, 50%, 50%. Here 50%, 50%. But here it's more like 90%, 10%. So this is a polar covalent, not polar bond, polar covalent bond. So both are covalent. When we share electrons, we are covalent. So begin first by telling what is the nature of the bond. Are we giving electrons to somebody? That's an ionic bond. Are we sharing electrons? That's a cationic. That's a covalent bond. Then when we share the electrons, are the electrons shared 50-50? That's non-polar because it's even. But when one is more than the other, there's gonna be polar. You're gonna have a polarization. The electrons are gonna polarize more around the bigger atom, and this will be more electronegative because all the electrons are shifting here, and this one is so poor, it's gonna become more electropositive. So that's a polar covalent bond. This polar covalent bond is very useful. It's very useful for water. Okay? Did everybody write that? Now, have we established what's an ionic bond? That's when Leo says Ger. You lose electrons, I take your electrons, that's a bond. Back in the day, the husband, he give the wife the money, she takes the money, that's the relationship. That's the ionic bond. Now it's a covalent bond. You give me 50, I give you 50, or something like that. Okay? So, ionic bond, one lose, the other one gain. That's the nature of the bond. But in covalent bond, both are sharing. Then, you're not done. Covalent, you still gotta tell. Are they sharing equally? Is there no polarization? Is the bubble equal in both sides? That's non-polar because it's even. That's non-polar. But if like oxygen is so big, having a relationship with hydrogen who's so small, all the electrons are going to be polarized. So the bubble around oxygen is going to be so big and around hydrogen is going to be so small. Let's hope we get luck today. Yay. Much better. Okay, now let's look at, so we already identified an ionic bond, we already identified a covalent bond, and now let's look at how useful is the covalent bond. So the relationship between oxygen and hydrogen, is that an ionic bond or a covalent bond? Between oxygen and hydrogen, is that a covalent bond or ionic bond? That's a covalent bond, very good. Is it a polar covalent bond or a non-polar covalent bond? That's a polar covalent bond. Very good. So that is useful to us now. Now let's look at water. Water looks like this. H2O. O with two little H's. O O with two H's and H here, O with two H's. So what is the relationship now? So water, when you look at water, water looks like this. O with two H's. O with two H's. Now how are they connected, the O with two H's? Now how are the charges? This is electronegative. Oh my God. The oxygen is electronegative. The oxygen is electronegative. The oxygen is electronegative. And hydrogen is electropositive. Hydrogen is electropositive. Hydrogen is electropositive. Electropositive. So the relationship in a pure water molecules, there's cohesion. Why is there cohesion? Because the negative, electronegative, or the electropositive are going to have a bond. And this is called the hydrogen bond now. So the H2O, that's a covalent bond. But between the oxygen and the other hydrogen of the other water molecule, now that's a hydrogen bond. Because it's between oxygen and hydrogen. They're not sharing. They're not sharing electrons. You see, they are sharing here. On this side, they are sharing. That's a covalent bond. But here they're not sharing. They have a weak bond known as the hydrogen bond. Here, there is a weak bond between the electropositive hydrogen and the electronegative oxygen. And that's the electropositive hydrogen and the electronegative. So the water molecules have two bonds. They have a covalent bond amongst the water molecule, H2O. But then the two H2, so this is a separate molecule. H2O, molecule number 1. It has oxygen shared, that's a covalent bond. Oxygen, hydrogen, oxygen, hydrogen. And here, oxygen, hydrogen, oxygen, hydrogen. Oxygen, hydrogen. And here, and that's a molecule number 2. Then there's molecule number 3. Okay, that's molecule number 3. Okay? That is molecule number 3. So these 3 molecules, the molecule itself is made up of covalent bond. But the 3 molecules, 1, 2, 3, they are connected to each other by what kind of bond? Hydrogen bond, where you have the electronegative oxygen having more relationship with an outside electropositive. And you have electronegative having a relationship with other molecule hydrogen bond. That's how it is. This is very important. You have a mental picture of how water molecules are in a solution. Among themselves, they have a covalent bond that looks like that, where there is a big bubble around oxygen, a little bubble around hydrogen. And here you see oxygen and 2 hydrogens, where it's really electronegative oxygen, the other 2 are electropositive. Then there is another type of bonding. So this is intra. This is intra. The covalent bond are intramolecular. Intramolecular. But when they bind with each other, that's intermolecular. And they bind to each other with hydrogen bond intermolecularly. And inside themselves, they have a bond that is intramolecular, that's covalent bond.
Can you repeat that again, please?
Okay, so I have H2O, water. H2O, water. H2O, water. Okay, don't write, just look, because you understand. Water, 2HO, 2HO, 2HO. These are three separate water molecules. So now let's look at inside them. How is the water molecule made? It is made by two covalent bonds, where oxygen gives one electron, hydrogen gives one electron, hydrogen gives one electron, oxygen gives one electron. But we said because oxygen is so big, it's gonna pull the electrons of hydrogen to spend more time around it. And that's what makes it electronegative. So now oxygen is gonna be more electronegative, and the hydrogen, because they are so little and so small, and their electron is being pulled away from them, that makes them electropositive. Is that point clear? So that's happening on every single water molecule. Every single H2O looks like that. Oxygen is so big, pulling all the electrons to its side over the hydrogen, making hydrogen more electropositive. This water molecule, it has oxygen, really electronegative, and is pulling all of the electrons to the side of oxygen, and then the hydrogens are so poor because they are positively charged. So that's the first type of bond. This is intra. Intra means inside, so that's between the water molecules. These are intramolecular bonds. Then, I don't just have bonds between the atoms making up for me the water molecule. I have bond between water molecule 1 and 2. But the bond between 1 and 2 and 3 is not covalent. They're not sharing ions. But what they are doing is, because this one is so electropositive and this one is so electronegative, the oxygen of atom 1 is going to start to develop a bond with the hydrogen of water 2. Because the oxygen is so negative and the hydrogen is so positive, but now we're crossing between molecules. So now there will be a bond between this electronegative oxygen and this electropositive hydrogen. Does it make sense? So that's now called hydrogen bond. Okay, so that's a hydrogen bond. So the bond between the two molecules is a hydrogen bond, and the bond inside the molecule, that's a covalent bond. So these hydrogen bonds are very important. We're going to learn later when we're doing the amino acids, and when we are doing the sugars, and we are doing the DNA, that the conformational change of the DNA, it's a double helix. That's how they stick together, with the hydrogen bond. That this one electropositive, that one has a hydrogen, then they bind together. So they start making conformational changes. So that hydrogen bonding is important for conformational changes of proteins. They are very important for conformational changes of DNA. So that's one usefulness. The other usefulness, yes?
Sorry, so do hydrogen bonds only happen when they are positively charged?
Of
Or
course,
is it-
yeah.
Okay.
Yeah, only when they are positively charged, and only with oxygen or maybe nitrogen who is electronegative. So they bond with between oxygen and hydrogen, or hydrogen and nitrogen. Very good. Yes?
So like it could only happen with an element that's like really negatively charged.
Yeah, and hydrogen. That's why they call it hydrogen bond. So it's always hydrogen, because hydrogen is so weak positive. All of its negative is being taken away by either nitrogen or oxygen. Then the other electronegative bond is going to have a bond with it. So we use that. It's very helpful for what? For conformational change, for the double helix of the DNA. And it's also important for solvation. So now let's talk about solvation. What is solvation? Not salvation, solvation. When we dissolve, solvation. When we dissolve. What happens in solvation is here, this. This is what's happening in solvation. So now, let's say I want to dissolve something in water. I put sodium chloride. Sodium chloride is a salt. Sodium chloride is a salt. And this salt is very important because sodium chloride looks like that. Sodium chloride. And is that how the molecule looks? Does sodium chloride look like that? No? What does it look like in terms of bonding? NaCl, but what are the charges? Don't forget that our charges, they don't look like that.
Positive.
Yeah. So when they were alone, sodium looked like this, chloride looked like that. But when they bond, so now sodium is neutral. Now sodium is neutral, chloride is neutral when they are alone. But when they have the bond, if you make it look like that, that's a covalent bond now. Because they are sharing electrons. But they're not sharing. They are what kind of bond? Ionic. So somebody is losing, oxidized, reducing agent. Somebody is gaining, reduced, oxidizing agent. So who's oxidized? Sodium. So what charge is that? Positive charge. Very good. What charge is chloride? Negative charge. So now, when I put it in water, water looks like this. O with two H's and I have O with two H's and I have O with two H's. Now what's going to happen is, don't forget, there is a slightly positive negative charge next to the oxygen and a slightly positive charge next to the hydrogen. You remember that? Slightly positive charge hydrogen, slightly positive charge hydrogen, slightly negative charge oxygen, slightly negative charge oxygen, slightly positive charge hydrogen, slightly positive charge hydrogen. So the intermolecular force between sodium chloride and ionic, the intermolecular force between OHs in water is covalent, very good. But when you add them together, the oxygen will say, sodium, I see that you're positive. You have a relationship with minus chloride? No. I am more negative than chloride is. Have a bond with me. Then the hydrogen will say, hey, I see that you're negative. You're bonding with positive sodium. I am more positive than sodium is. So now, the negative oxygen of the water is going to bind with sodium, and the positive hydrogen of water is going to bind with the chloride. And that's how you dissolve salt. That's how salt disappears. Salt disappears because the positive sodium is going to go to the minus oxygen. And the chloride is going to go to the positive hydrogen. That's how we break the bond, and now they disappear. But when I boil water and the water dissolves, so the bond between oxygen and sodium are gonna disappear. Between oxygen and sodium are gonna disappear, and then this bond is gonna return back again. Very important for you to understand how solvation happens, how water dissolves things. It dissolves things relying on this slightly electronegative charge. So if we have calcium chloride, CaCl, same thing. Oxygen is gonna say, hey, don't be in a relationship with chloride. You want somebody negative? I'm the most electronegative. And then the hydrogen will say, oh, don't worry, I am the most electropositive because oxygen is the biggest bully who takes all the electrons away. I'm the most electropositive. I will be a better substitute for you than sodium or than calcium. And then they're going to have a bond. And that's how we dissolve things. Very important. Are we done? Okay, now we're gonna move on after that to the properties of water. So now we talked about water, then we're gonna talk about the properties of water. Water are universal, versatile solvent. Water dissolves, they are versatile. They are versatile solvents. Okay, so the first property is water dissolves other solutes. The second property, what's the second property? Water has very high specific heat capacity. We use it for thermal regulation. Remember last week when we talked about homeostasis And when it's so hot, you have sweat all over your body. So that sweat is able to, that sweat has a lot of water in it, because water has high specific heat. So that means it takes a lot of heat to make water molecules evaporate. Okay? The other thing is that water have cohesion. They stick together. You see how the water molecules, they used to stick together? And the hydrogen plus with the oxygen minus, and hydrogen plus with the oxygen minus, unless you put another salt that they're going to replace the bonding. But they are in cohesion. Also adhesion. You're going to learn in anatomy and physiology too that the heart has a capsule, a fibrous capsule, a fibrous bag, and the bag is full of water to hold the heart from any trauma or the lung also, that there is a fibrous tissue with water on it. So the water has cohesion, adhesion. We use it for thermal regulation because it has high specific heat capacity and it dissolves. And we also use it for hydrolysis. So now for chemical reactions. So now this is the part we have been doing, chemistry, the atoms, the mole, the Avogadro's number, all of this. Why? So now we can finally get to the structure of our macromolecules. So now you can finally be able to tell how the macromolecules will fall. I mean, imagine you study anatomy and physiology, you don't even know what an amino acid look like. You don't know what a nucleic acid looks like. You don't know what a fat looks like. You don't know what the sugar, carbohydrate looks like. I'm teaching anatomy and physiology in another school, part 2, anatomy and physiology 2. This student don't know what an amino acid looks like. I never asked you to draw for me glutamic acid, that's one amino acid. I never told you to draw aspartic acid. I never told you to draw glycine. Just be able to recognize it. That's like you don't know the difference between a monkey and a human being. I'm not telling you what kind of monkey. Is it a chimpanzee? Is it a orangutan? I'm not telling you what kind is it. Just know what it looks like. They don't know. So you have to know how they look like. I'm not going to give you like an assignment or on the exam ask you, what's the name of this amino acid? Is it glycine, aspartic acid? I'm not going to ask you for its name. You don't need to memorize that. But am I going to give you a structure and tell you, is it a fat? Is it an amino acid? Is it a sugar? Is it a nucleotide? You bet. You will definitely have to know the structure of what a fat looks like, what an amino acid looks like, what a nucleic acid looks like. You don't want to be like the students in that other school. Okay? So now we're going to go into the structures of our macromolecules and micromolecules. We gotta find another class, really. We're gonna have to find another place to do this illustrations, because I'm gonna go try to speak too. Okay, the first so what's a macromolecule? So before we get to micromolecule, we have the concept of metabolism. So that's why we have metabolism. In metabolism, we have two processes. Either we have a big molecule that is made up of 1, 2, 3, 4, 5, 6, 7, 8 pieces, and we break it down into 8 on its own, 7 on its own, 6, 5, 4, 3, 2, 1. So we break them down through catabolism. So catabolism is when we break down the molecules. Anabolism is when we build them up. That's anabolism. So you can tell we use anabolism for storage. If we have a lot of glucose, if we have 8 glucoses, we stick them up together, we stack them up, we stack, and store for storage. We store with anabolism, so they stick together. Okay? So that is known as anabolism. Anabolism. and we break down through catabolism. This is so important. So why do we break down? We break down because the bonds have energy. So there is energy inside the bond. The bond of the fat that I eat, the bond of the protein that I eat, the bond of the sugar that I eat. The bonds have energy. I need to get the energy out. I need to make the energy exit. It's called exergonic. Exergonic. So in order for the energy to exit, how do I make the energy exit? By breaking the bond, and I break the bond with heat. So I supply heat, that's called delta H, or the enthalpy. The enthalpy is heat, enthalpy. Enthalpy is delta H, heat. So if I want to break the bond, what I do, I heat it up or make it cold? I heat it up. So I put plus delta H or minus? Plus delta H, excellent. So I add heat to break the bond. When I break the bond, the energy will exit from the molecule, exit to me. So now I have energy. Energy for me to go and exercise. Energy for me to run my metabolic activities. And that is known as exergonic. So that's the bond. That's me. So exergonic, it exited the bond to me. So now that's exergonic. The opposite is when I have enough energy. So I need to store. So here in catabolism, I broke down in catabolism to get exergonic energy, to get the energy to come out. So I break down in catabolism to get the energy to come out. Then I use heat to break down the bond, and then the energy comes out to me, exergonic. But let's say I already got enough energy, but I have so much sugar in my body, now I cannot use, because there's no requirement for me to use, I'm not running a marathon to make myself use all of the sugar. So now I need to store it. If I need to store it, stack it up, do I need to build bonds or do I need to break bonds now? I need to build bonds. So if I need to build the bond, if I break the bond by putting heat in, I build the bond by getting heat out. Very good. That's minus delta H. Minus delta H. So when the heat comes out, the bond is formed, then the energy leaves me and it enters into the bond, and that's known as endergonic. Endergonic. So in anabolism is endergonic. Okay? Is endergonic. And the name for enthalpy is when I put heat in, that's endothermic. So the temperature is going in, endothermic, but the energy is coming, exiting, that's exergonic. Here, when I want to build up, the heat is coming out, that's exothermic. But the energy is returning, leaving me and entering the bond, that's endergonic. So you need to understand that anabolism is storage, building, stacking up together, making the bonds. Endergonic, exothermic. Exothermic. While in catabolism we break down the bond, and so that's catabolism, breaking down the bond, endothermic and exergonic. Okay? Yeah. You're gonna go home, read the slides, rewatch this, and it's gonna make sense to you. Yes?
Is it endergonic?
Endergonic, yeah.
Or endogonic?
Endergonic.
ER?
ER, yeah. Okay. All right. So now let's look at the structures of our amino acids. So the amino acids look like that. Carbon, they have an alpha carbon. Let's say I have 3 amino acids. Each of them has an alpha carbon. They have 4 terminals: north, east, south, west. North, east, south, west. North, east, south, west. That's amino acid number 1. That's amino acid number 2. That's amino acid number 3. Okay. Each amino acid, all of them, they have 3 out of 4 the same. All of them have a hydrogen in one of the terminals. All of them have a hydrogen. So that's not different. They all have that. All of them have an amino terminal, N with 3 H's. N with 3 H's. N with 3 H's. And N with 3 H's. So they all have that. That's common. Then they all have a carboxylic terminal. A carboxylic terminal. And a carboxylic terminal. Then, when I have the carboxylic terminal, so that's how they look. So now they are separated, right? Are they attached? They're not attached. They are separate. So what's different? That's the R group. That's the fourth terminal is what makes them different. R1 is different from R2, is different from R3. So they have three things in common. It is just that one last R group that makes them different. Now, they are all separate. Now they are here. One is separate from two. If I want to build them up, you see here, this terminal has an OH. And the other terminal, so the one terminal from the carboxylic, that's called the carboxylic terminal. And the N terminal is called the amino terminal. That's the amino terminal. That's the carboxylic terminal. In the carboxylic terminal, that's OH. On the amino terminal, that's an H. Interesting. That looks like who? Water. H2O. So now I subtract, take out water. H2O, known as dehydration. Dehydration. So when I get the OH out and the H out, then a bond will be made between them. Now I stuck them up together. I condensed them. That's why it's called condensation. Condensation reaction or composition. So I composed them together. Composition. So now they stuck together. When they stick together, this bond is called a peptide bond. This is money. This is golden. The peptide bond. The peptide bond is what connects the amino acids. And how do we get peptide bond? We removed water by taking OH from the carboxylic terminal and H from the amino terminal, and now we get H2O out. Let's do it over here on the other side. I want to connect one more. This amino terminal will take one H out, thank you. Then the carboxylic terminal will take an OH out. So now that's H2O. So now the H2O will come out, will take out H2O, known as dehydration, or known as condensation, because I condensed them together. Condensation and composition. Composition. So now they stuck together. They stuck together. Composition. So that's a peptide bond. Peptide bond. So now that's me going from here to anabolism. That's how I stick together. Peptide bond, peptide bond, peptide bond, peptide bond. I make peptide bonds while water coming out. Let's say now it's time for me to break down. That is when I wanted to store things up. When I wanted endergonic. When I wanted storage. Now I'm starting to run the marathon. I need energy. I'm not going to be storing. I'm going to be using what I've been storing. So now I need to break the peptide bond. If I make the peptide bond by getting water out, how do I break the peptide bond? By adding water in. So now I bring water plus H2O, and I say, OH, I need you back where you belong, OH. H, I need you back to where you belong, H. And now I separated the bond. So it's now no longer peptide bond. I say, plus water here. And plus water is H2O, H and H. So OH comes here, OH comes here, and H comes here. Now I separate the bond. So now separate. So I separate with plus water, and it's known as hydrolysis. Hydrolysis. I use lysis to cut. So I cut with water. By giving OH to the carboxylic, H to the amino terminal. I cut it up. And now that is known as hydrolysis. You need to know that. You need to know that dehydration, I get the water out, condense them together, I stick them up together, that's a peptide bond. If I want to break it up, no problem, I do the opposite. I do hydrolysis, I add water, plus water in, OH to one side, H to the other side.
And that's metabolism?
And that's when I break down catabolism, yeah. So now I'm adding water to break down. Excellent, very good. That's peptide bond. That's protein. We are done with proteins. We have now sugars. And we have also, let's do some slides, and then I think we have done enough whiteboard illustration. Let's now do the slides, and then we're gonna revisit these concepts again we're gonna revisit these concepts again when we are doing the PowerPoint slide. There are better illustrations on the book.
It was nice this morning, the new one. Carrying the big phone bracelet is really cold.
I swear a lot, I never break last night.
But today I was grabbing
Yeah, I gotta start using one in my bag. Like a pair of leggings and then I just put them in the garden.
Okay, yeah, that could be off now. You can turn it off. Thank you so much.